In this video, we will derive the equations for the velocity and acceleration of a particle in the Pathline coordinate system. So far, we have been describing the motion of a particle using a rectangular coordinate system that does not adjust its orientation as it moves along the path. We usually call this the xy coordinate system. However, when a particle moves along a curved path, it is sometimes more natural to describe its motion using a coordinate system that moves with the particle. We will call this the pathline coordinate system. In the pathline coordinate system, the t-coordinate is always tangent to the particle path and is pointed in the direction of motion. This means that the t-coordinate is always pointed in the same direction as the velocity vector. We'll call the unit vector in the t direction e sub t hat. The n, or normal coordinate, is always perpendicular to the t-coordinate. We'll call the unit vector in the n direction e sub n hat. Notice that as the particle moves along a curved path, the orientation of the pathline coordinate system changes. That means the unit vectors for the t and n coordinates change as a function of time. The local radius of curvature, denoted by the symbol ρ, gives the curviness of the path. As the local radius of curvature decreases, the path becomes curvier. The n-coordinate always points in the direction of the local radius of curvature. Now we'll derive equations for the velocity and acceleration in this new coordinate system. The velocity vector is always tangent to the path. This means that the velocity vector only has a component in the t direction, and we can write the velocity vector as the speed v times the unit vector in the t direction, e sub t hat. Now we zoom in closer and examine a particle as it travels along a path for a very small amount of time, dt. Initially, the particle is at point 1 and has a velocity v1. After the time interval dt has passed, the particle has traveled a distance ds and now is at point 2. Its new velocity is v2. The local radius of curvature ρ gives the curviness of the path and does not change significantly in such a small amount of time. The angle that the particle passes through during this time is d beta. The magnitude of the velocity is the distance traveled over the time elapsed, which is ds divided by dt. Assuming that the radius of curvature does not change significantly during this small time dt, the arc length from 1 to 2, which is ds, is equal to ρ times d beta. Plugging this expression for ds into our equation for velocity, and rewriting d beta dt as beta dot, we now have an expression for the velocity in terms of the local radius of curvature and beta dot. The acceleration vector is the time rate of change of the velocity vector. Plugging in the expression for the velocity vector, and then using the chain rule, we obtain v dot times e sub t plus v times the time rate of change of e sub t. We just found the speed v is equal to ρ times beta dot, but we need to examine how e sub t changes with time. Since e sub t is a unit vector, its magnitude does not change and is always 1. However, the direction of e sub t does change with time. Let's draw the tangential unit vectors in blue at points 1 and 2. And examine these vectors more closely. During the time dt, the unit vector changes by an amount d e sub t as it swings through an angle d beta. d e sub t is pointed in the normal direction. The d e sub t vector is equal to its magnitude times its direction e sub n. The distance traveled by the tip of the tangential unit vector is the arc length, which is the angle d beta, times the length of the e sub t vector. The length of e sub t is 1. Dividing the expression for d e sub t by dt, we now have an expression for the time rate of change of d e sub t. Going back to our expression for the acceleration vector, we plug in the expression for d e sub t dt. d beta dt can be rewritten as beta dot, which we previously found is equal to the speed divided by the radius of curvature. And we finally arrive at an expression for the acceleration of a particle in the pathline coordinate system. Taking a closer look at the equation, we see that the total acceleration is due to the acceleration in the direction tangent to the path plus the acceleration normal to the path. The tangential component is labeled a sub t and is equal to v dot. The normal component is labeled a sub n and is equal to v squared divided by rho. The magnitude of the acceleration is the square root of a sub t squared plus a sub n squared. A closer analysis of the two components give insight into how they change a particle's motion. V squared over rho will always be greater than 0, so a sub n will always be greater than 0 as well. This means that the normal component of the acceleration will always point in the positive n direction. Since the n direction is normal to the path, a sub n causes the particle to change course, just like a steering wheel. V dot can be either positive or negative, so the tangential component of the acceleration can be positive or negative as well. If v dot is positive, the tangential acceleration component points in the positive t direction and the particle speeds up. If v dot is negative, the tangential acceleration component points in the negative t direction and the particle slows down. This component is responsible for the particle changing speed, just like a gas pedal or brake pedal of a car. Let's look at two situations where the tangential component doesn't change sign. In the situation on the left, a sub t is positive all along the path, which means the speed always increases. The acceleration vector always points toward the forward direction. In the situation on the right, a sub t is negative all along the path, which means the speed always decreases. The acceleration vector always points toward the backward direction. In both cases, notice that the acceleration vector must deviate from the path in order for the particle to change direction. If the acceleration vector is parallel to the path, a sub n is 0 and the particle travels in a straight line. If a particle is restricted to move along a circular path, we obtain a special form of the velocity and acceleration equations. Notice that the radius of curvature is constant in this case. For this situation, it is common to replace the radius rho with r and the angle beta with theta. The expression for the speed becomes r times theta dot. Plugging in this expression into the equation for a sub t, and pulling r out of the derivative because it is constant, a sub t is equal to r times the angular acceleration theta double dot. Plugging in the expression for the speed into the equation for a sub n, we find that a sub n is equal to r times the angular velocity squared, or theta dot squared. In many situations, the angular velocity theta dot is replaced by the symbol omega, and the angular acceleration theta double dot is replaced by alpha.